Okay, so lecture 6, this builds upon what we've been doing, of course, and today we've got transducers. Finally going to get to transducers. So in case anybody missed it, we got a really nice lecture, supplementary material on diffraction and Huygens principle and some math with a very cool result. We'll mention some of those results as we keep going, but I definitely want to refer you back to that supplementary material if you're interested. So what we want to talk today, first of all, is about transducers, and we can broadly separate these into single element transducers versus arrays. And of course, what are the advantages of a single element transducer? They're cheaper, they're simpler, you only need to drive one channel, and the focal spot location and size is relatively fixed. You can split those into flat or planar transducers and then curved and focused transducers. And then there's arrays. So they're more expensive, they're more complicated, but the plus side is you can move the focal spot around. You can electronically focus and do phase aberration corrections. You can defocus to make the focal spot bigger. What have I missed, Keith? I'm sure there's other trade-offs here as well.
Well, I was going to ask you if we talk about how you can use acoustic lenses to almost dynamically steer a single element, depending on just, which lens you pick. Did we get into that?
No, I wasn't going to really cover that, but that might be a good project for someone.
Yeah, and we can even mention it before arrays. It's almost like a pseudo array. Not quite, but
we'll have a chance later to talk about phase aberration correction. So maybe that's the right time to bring it up.
Cool. Sounds good.
Okay, so what do you use? You don't actually use a big transducer because you've got the one that you showed us in lecture 5 that's built into that little cannula.
Yeah, so I mostly use single element. It's sort of a focus because it's a ring, and with a ring, and if you do the Fourier transform, you'll get a little focus at a distance that's relative to the internal diameter of the ring. But I also have experience in developing arrays, and today Kim and I thought, based on your feedback in class, that we would sort of walk you through the practical aspects of selecting an array that's right for your application. So I think that's at the end of the lecture.
That's at the end of the lecture because we got to go through some theory first. So we're going to bring in the lecture that we'll bring in the lecture that we used last year that has all the theory. And then the new part is going to be the practical aspects. So let's get into that. This is the outline for today. Single element transducers, planar and focus. We're going to get into some key aspects of, focal spot size and things like that. And then we'll get into arrays. And it's really important with arrays to talk a little bit about side lobes and grating lobes and how that's going to impact what we do. We'll talk about those the rest of the class probably. And then lastly, we'll do that practical aspect, finding the array for you.
Yeah, Kim came up with that name. I thought it was great. Arrays and you.
Okay, so let's get started. First of all, what do we care about? Keith, what do you care about when you choose a transducer?
When I'm looking at a transducer, it's all about the focal point and what that looks like. How wide is my beam? How long is it? And how far away from the transducer? Because again, the whole point of this course is not to affect things on the way down.
Right. You care about the focal depth?
Oh, sorry. I should have, begin with the focal depth is my favorite.
Yeah. And, so you're going to pick a different transducer probably based on the focal depth alone. That's true. Yeah, the focal length and the focal width. So those are the characteristics of the focal spot itself. All right, what do we have to tweak? Oh, and sometimes the divergence angle. I don't think that that's something that we really care about so much, but there's a nice equation for the divergence angle in the far field, so I mentioned it, but I don't think it's something we care about.
We do. I think there's problems have come up where there's stuff past your target, like you'll hit the skull and that'll resonate. You might hear the ultrasound or something like that.
Yeah. Well, we definitely care about the far field. That's true.
Oh, okay. Is this not part of the far field?
Oh, it is. It is. It's just sort of what's the divergence angle. It can either diverge very slowly or diverge very quickly, and like how quickly. And actually, if it diverges with a larger angle, then that's going to spread the energy out. So that actually could be beneficial, spreading the energy out.
And a question, is the divergence angle always the same as the convergence angle, or can they be different?
No, I think it's similar.
Okay.
Yeah. Okay, what do we have to tweak when we pick a transducer? We already mentioned the diameter. The diameter is something we can, like what knobs do we have to control? There's diameter. What else?
Well, if you have a curved single element, then you can control the radius of that curve.
Yeah, the curvature. And I'll define F number in just a moment. And then lastly, there's the frequency.
Mm-hmm.
Yeah. So, and that's the fundamental frequency. Okay. So those are our knobs we have to tweak, and then they're all going to play into the characteristics of our focal spot. So I wanted to go through that a little bit. First, planar just means, of course, that the transducer is flat. And then focused is the transducer. The transducer, remember last time we talked about the silver part being the transducer. There's electrodes in the front and the back, and then there's a matching material. The matching material has to be a quarter wavelength. And so, and this one looks like it might be a little thicker, but that just looks like it's thicker on the edges, and then it gets sort of concave in there. But this is now the focus transducer. And then usually the focus transducer, you get a really nice focal spot. So I just wanted to show an example right there. So it's just kind of knew where we were going.
So Kim, would you say it's more often or just sometimes that they use the matching layer to create the focus, or is that supposed to be your piezoelectric in your image?
So I think the matching layer needs to be a quarter wavelength. And so it needs to be a quarter wavelength throughout. So you can't have it be thinner in the middle and thicker on the edges.
Okay, so it would always have to be the transducer with curvature or some sort of other.
Or a lens, potentially.
Okay.
Yeah. Okay, so let's talk about our planar transducers. So in this simulation, I have two transducers that have different diameters. So the second one is twice the diameter of the first one. And we see the beam plots for each of them. So there's the area in the Fresnel zone, which is kind of garbagey, and then the Fraunhofer zone, which is which is very smooth and nicely well behaved for each of them. So how do they compare? Well, first of all, let's look along the on-axis profile in order to look at the focal depth. And what we see is the focal depth for the smaller diameter is closer to the transducer. So in other words, what our equation says is as we increase the diameter, we're going to increase the focal depth. And that's what we see borne out here in these simulations. We can also see the relationship with frequency. So now let's convert this in our minds. If we increase frequency, that means we're decreasing wavelength. As we decrease the number in the denominator, that means that the whole number goes up. So focal depth is increasing. Increased frequency gives us increased focal depth.
So Kim, if my target was just a little bit further than my focal point, I could either increase frequency or diameter to reach that target better. Is that right?
That's right. And let's say you're using a transducer, which is just giving you a focal depth, which is just a little bit short. Then what we learned last time is that you can drive that transducer at a little bit higher. You'll have some loss of intensity, as long as it's still sort of within the bandwidth of the transducer, a little bit loss of intensity, but then you can drive it a little bit higher and that'll give you a little bit longer focal depth. Mm-hmm. Yeah, that's perfect. All right, so let's talk about the characteristics of the focal spot. So we care about the focal width and the focal length. First of all, focal width. So here, what we're going to do is we're going to say, well, at the distance of the focal depth, we're going to plot along those profiles. And we see that the larger diameter transducer at the longer focal depth has a larger focal width compared to the smaller diameter transducer. So normally, you can use equations potentially, but normally in my lab, we would just make measurements of our focal spots in order to verify these. So how do we make a measurement? Well, we'd use a hydrophone, which would be a way to scan around and measure. And then the key question here is when you're measuring the focal length and focal width is how do you define it? And then normally we would define it as the full width half max when you're looking at intensity. And so we're saying when does the intensity go down to half of its value? And so then since to get to pressure, we take the square root of that, then we're saying what's the square root of 0.5. And so we're looking at the 0.7 point on the pressure. So on these plots, I was looking at 0.7 and saying what's the width at 0.7. And so that's where I was seeing That's why I drew those lines when I did. Now the focal length, we're expecting to see something very similar. We're just looking in the other direction. So again, plotting the same plots that we saw before, and then we're going to look at the 0.7 point and say what's the width of those two beams. And you can see that the smaller aperture beam has a smaller focal length than the one that's larger. Okay, now we could also come up with some equation here for the divergence angle of the beam. And again, I'm not totally sure, exactly when. We don't in my lab care that much about this, or we don't talk about it too much. I did calculate it there for those two beams. And so with the larger diameter, the relationship is 1 over the diameter, and it should give you a smaller angle, and that's what we see there. All right, so let's get on to focus transducers. Mostly what we're using is focus transducers. So let's make some definitions first. So one definition is the radius of curvature. So if there's like you can think about this as being part of a circle. So let's have a figure down here. So let's say we have these two transducers, and these now have the same radius of curvature. They are part of a circle, as you can see here, and then the radius of that circle is the radius of curvature, and that's typically the focal depth. So the focal depth is about the radius of curvature. Now in this situation, these two transducers have different diameters. So one of them is just got a larger surface of that sphere, of the circle, than the other one does. So the definition of F number, which is very, very useful here, is just the radius of curvature. So that tells you about the curvature, and then divide by the diameter. So these two transducers now have different F numbers. Keith, which one has the larger F number?
So the red line has the same radius as you mentioned, but a smaller diameter. So that would mean it has a larger F number.
That's right. And so the larger the diameter, the smaller your F number. And what we see here is that the larger diameter transducer is actually going to have a little bit better focusing than the smaller diameter. So as the F number gets smaller, then it's going to be more focused. All right, so again, we care about the same things. We care about the focal depth. We've already talked about the radius of curvature. We care about the focal width and length. So here I've done a situation where we have the same diameter for each of those transducers. Simulation is the same diameter, but what I've set up now, again, getting back to Huygens principle, is that I can set up my simulation as multiple individual points, and each is a spherical wave. And what I've done here is change the phase of those spherical waves, so it's simulating as if there's a curvature on that single element transducer. What we see as we go down here is a little bit of curvature, there's more curvature, and then more curvature. And then what we see as the result is that when there's not very much curvature, the focal depth is further away. We expect that. And as you increase the curvature, the spot comes closer and closer towards the transducer. Then in terms of the focal width, it's related to the F number times the wavelength. So with the smaller F number, then it's going to have a smaller width. And then the focal length is also related to the F number. So the smaller F number, as we see in the lower plot, gives us a smaller focal spot, both length and width. So that pretty much tells us how we can manipulate with our single element transducers what our focal depth is. And given a focal depth, it pretty much tells us what the size of the focal spot will be. And we don't really have a lot of control over the size of the focal spot. So in some ways, it's sort of a little bit out of our control. And this is showing us that, let's say we have a head and we want to get deep inside the brain, then ultimately we're going to use a transducer that's going to give us the focal depth that we need. And unfortunately, it's going to give us a larger focal spot than we might want. We can go down to smaller focal depths and we get smaller focal spots. So it's a bit of a trade-off there.
So F number is really like a scale-free metric, though. I mean, I could envision just having a really huge transducer with the same F number as our smaller beam up top here, and you can get that smaller beam very deep in the brain now.
Yeah, I know in some sense that's sort of what the Insight Tech system's trying to do, where you use a transducer that's a whole hemisphere. And then it has a pretty small F number because it's got the large diameter compared to the radius of curvature. And so that's going to give you the smallest spot possible for that focal depth. Yeah. Yeah, so at any rate, it's always going to be some trade-off there. And so what about the frequency dependence? So as we increase our frequency, that's going to decrease our wavelength. And so decreasing wavelength is sort of like decreasing our F number. So it's sort of like increasing frequency as we come down on the plots. Increasing frequency is like a decreasing F number. So this is going to be a higher frequency down here than up here. So that is something that we can do, is go up in frequency, given a certain diameter of the transducer. But then it comes closer. So we still have that sort of trade-off of depth and focal spot size.
Mm-hmm.
Last time we were talking about focused transducers, and in particular we talked about the F number, that's the radius of curvature over the diameter, and we talked about the focus, and it's really helpful to have equations for the focus so you can kind of think through, well, what if I do this and what if I do that? So the focal width is related to the F number times the wavelength, and the focal length is the F number squared over the wavelength. So here we ended the lecture recently with last time with going from higher F numbers to lower F numbers. And the way we did that was that we changed the radius of curvature. So you can see here, it wasn't very curved. And then as we went to more curved and then more curved, and we see that the focal spot came closer to the transducer, but also the focal width and focal length decreased at the lower F numbers. So that's cool. One of the things you said was, hey, why don't you superimpose the color red? So I did that, made it red, and I superimposed it on the brain. So that was kind of fun to see. You know, it's such a struggle to think about trying to do neuromodulation in the brain with these large focal spots.
Yeah, and what do people usually refer to those spots as, like cigar shaped, right? You'll probably hear that a lot if you're reading the literature. It doesn't really look very much like a cigar, though. It's more like a thin streak for this particular wave.
Well, don't forget, this is a, circularly symmetric. So, it's a bit long for a cigar, but yeah, I get your point. Sometimes they say it's,
No, it was just a joke. I was just saying I wouldn't smoke that cigar. I don't know why. Anywho.
Okay, let's keep going. So here what I'm going to do is I've got the same thing where I have higher F numbers to lower F numbers, but what I've done now is I've just changed the diameter of the transducer so that you can see as we go to a larger diameter, since it's in the denominator, then that decreases the F number. And then the simulation is showing you that even though we're focusing further out, that the focal width and focal length are decreasing. So that's really nice. If you want to get deep in the brain, looks like you need to use a larger transducer. I think, oh yeah, I even superimposed them there. So this is a case where, deeper in the brain with a larger transducer was more possible.
And these beams, they don't look like the most amazingly specific things ever, but you have to remember we're comparing these to technologies like TMS and TDCS, where you're blanketing the entire cortex in a giant field. So it's actually remarkably specific in comparison.
Yeah, and the other thing is that we haven't finished talking about all the possibilities. We haven't really talked about frequency that much, and we haven't really talked about what phasing can do for you. So there's still more to come.
Are you trying to tell me right now, Kim, that we can do better than these long cigar-shaped beams?
Well, taking frequency into account, that's possible. And then there's the possibility that there's other ways to do it as well. But it is something to keep in mind that the larger the aperture, the smaller the focal spot. So that's something that we might come back to later. All right, so we talked last time a little bit about single element versus arrays, and today I'm going to talk more about arrays. You know, they are more expensive, they're more complicated because you have multiple elements you're going to drive independently, so you got a lot more electronics. But really, the promise here is being able to move the focal spot, so that's what we're going to talk about later today. And then later lectures, we'll talk about phase aberration correction. All right, so simply a couple things to talk about: arrays, grading lobes with linear arrays, and then we'll talk about phased arrays and more about grading lobes. So yeah, let's just get right into it. So first of all, some definitions. So the idea is if you take a crystal, that's a single crystal, and you use a saw and you split it up into multiple elements, now you can drive each of them independently. It's the same idea. You put electrodes in the front and the back and drive them independently. Just the directions, if you're coming straight out from a, let's say it's a diagnostic ultrasound transducer, straight out is the axial direction. Along the length of it is the azimuthal, and then in the perpendicular to the direction of the long direction. So in the short direction of a diagnostic ultrasound transducer, it's called the elevation direction. I'm not going to get into all the details of the diagnostic imaging, but every now and then I just kind of want to bring it back to that language because the therapeutic ultrasound kind of comes from the diagnostic ultrasound field. So sometimes we still use that same language.
And are they always rectangular elements, or are they cut rectangular, or are there other variations on that?
Well, for diagnostic ultrasound, oftentimes we think about them as sort of rectangular. What we're going to see in just a moment for our therapeutic ultrasound or ultrasound neuromodulation is they can be all different geometries. So hang on just a moment with that question. I also wanted to sort of define the overall aperture. So the aperture is the overall size of the whole thing, the length of the whole a set of elements. The width is the width of each element, and then the pitch is a very important number. So the pitch is sort of the distance from the center of one element to the center of the adjacent element. And the pitch is really important because that's going to play into the grading lobes and the location of those grading lobes that I'm going to talk about. The kerf is the spacing between them. I think that's probably important for some fields. It's not something I end up talking a lot about, but pitch is. All right, so let's just talk very briefly about array beamforming. Let's say you have 5 elements that are lined up, and if you don't do anything special with respect to the phase, and so in other words, they all have the same phase as the ultrasound comes out, then you can see there's little spherical wave fronts. And then if you sort of sum them, especially in the far field, then you're going to get a constant a plane wave coming out. And so that's what we saw when we had those 5 elements and we set up the simulation for those 5 elements. And then you can see that there was a constant plane wave. And then in the far field, you could see that there was the constructive interference that gave you a beam, and then the destructive interference so that you got that nice beam. So the nice thing now, what you can think about doing is just phasing the elements such that there's 2 different ways to think about this. You can think about it as a delay or a phase. And in diagnostic imaging and diagnostic transducers where the number of cycles was really small, like maybe 3 cycles, then they would just use a physical delay in the system in order to have these center elements be delayed compared to the outer elements. With therapy, because the ultrasound's on for a very long time, many, hundreds and thousands of cycles, that we tend to think of it more as a phase. So the phase of the elements with respect to each other, but ultimately it's the same thing, because remember when we had that equation for the sinusoid, we had kx minus omega t, and that's the phase, and you can change the phase either by delaying the wavefront or by adding a constant term. So it's essentially the same thing. But what we're going to do here is we're going to put a phase that's different on each of the elements, and if we put a quadratic phase across those elements, then what we see is that when the wavefronts come out, then they basically get focused, and they'll get focused to the point. And so that's what we saw last time. Right, I just kind of wanted to go through that again because I'm going to show you in just a moment how we're going to build upon this way of thinking of it. The thing I didn't talk about last time is what happens in diagnostic imaging. Let's say you have a lot of elements in here, and then you would pick some smaller set of them, what's called a sub-aperture, in order to make a beam and to interrogate one line of the image. And then you would translate over which subset of the elements you're using to make a different line of the image. So to interrogate that line, listen to the echoes coming back. So in other words, we're gonna build up the image one line at a time in diagnostic imaging by using a sub-aperture of the whole set of elements. So that's what's shown here, is that just another way of saying sort of the same thing is if you have an array with a large set of elements, and this is for diagnostic imaging again. So we have an array with a large set of elements. We're going to set up a sub-aperture with a subset of those elements, just enough to give us the beam that we want. And maybe there's going to be some phasing on those elements so that we can get kind of a nice beam. And remember, there was some time ago, we saw an ultrasound image of the fetus that was sucking his thumb, and there was a focus that was indicated on the image. And so what you do is you set up the phases of these elements to get the focus that you want, the focal depth that you want. And so that's how, yeah, go ahead.
The image quality and the signal improve as you're reading from points in space closer to the focal point?
Yeah, absolutely. Because what you're going to see is that when the beam is really small, you're going to get a crisper image. And when the beam is really big, then it kind of blurs out. And I think you will see that in just a moment. Yeah, in fact, right here. So let's say this is the field of view that we want to image. Then we'll use our sub-aperture in order to interrogate the first line of the image. Then we'll move that sub-aperture across the image in order to build it up one line at a time. And what you can see is that for that first line, there's a smaller amount of tissue that that gets measured, that you receive echoes from at the focus. But if you go either sort of near field or in the far field, that you're going to see that there's going to be a lot more blurring due to the fact that the beam gets thicker. So the field of view is necessarily going to be smaller than the array size, because some of these elements over here contribute to that first line, but you know, they're just sort of lost after that. So really the half of the sub aperture, you know, like the whole array minus the width of the sub aperture is the width of the field of view that you're able to image, because you don't get any lines from half of that sub aperture out. Hopefully that made sense. I'm not sure I explained it perfectly, but I think graphically you probably get my idea. Let's say you have some object out there that you want to image, and as you're building up the image one line at a time, you can see that there's multiple lines that are, because of this has some width to it, there's multiple lines that are going to pick up that object. In fact, it's going to end up being blurred because of that width. So that's exactly what you were referring to. The wider beam means that one object goes into multiple lines, and it sort of lowers the resolution. And then in diagnostic ultrasound, there's going to be a choice of the sub-aperture size. It presents a trade-off between resolution and field of view. So the larger your sub-aperture, the smaller your focal width. That's what we saw before in those prior slides, and that would be good. But then the larger your sub-aperture, the more lines that are lost that don't contribute to your field of view. So you have a smaller field of view. So there's a bit of a trade-off there. All right, it's a little bit of a digression into diagnostic imaging, but you know, I think that in terms of the transmit side and the sub-aperture, that's kind of a useful concepts that we'll find useful as well. But just like you mentioned, a lot of the arrays that we use are going to be different geometries. So these are two of the arrays that we use in my lab. One of them is a flat array, and it has 1024 elements. So this was about 3 to 4 inches across at the square part, and then divided up into, you know, as I said, 1024 elements. So each of the elements is pretty small. And then they're just kind of placed on the Cartesian grid. Although you can imagine that you might have some set of elements that's not even necessarily spaced regularly. This is another transducer that we have. It's, I mentioned this before within the context of the essential tremor treatment. So again, there's 1024 elements. They're placed around on the sphere. So this one was flat, they're placed around the sphere. The placement around the sphere gives it some nice geometric focusing already. With this one over here, there isn't any geometric focusing, but we can do all of that electronically. Both of them, of course, use water for coupling. This one is shown with a water balloon. So that's what makes the square a little bit hard to see, because in front of that, there's a water balloon that holds water that's used for coupling, but also used for cooling. So there's lines in here that circulates that water in and then out again to cool the transducer and also to cool the skin. This one also used cooling. We mentioned that before because the person's head is suspended in here, and then there's a membrane placed around their head, and then water is placed into the cavity, and that water is again chilled and circulated. Anyway, these are just a couple of arrays.
Is the heating that occurs largely from dielectric heating from the voltage on the piezos, or is it from the actual absorption of ultrasound in the near field by the tissue?
There's two things. There is the absorption of the tissue, and we really care when we're using high intensities that we don't get near field, skin burns. The other thing is that when you have continuous waves that are on for a long time, you can have heating of the elements themselves. Yeah. And even with an air-backed system, you might only have 50% efficiency, which means that 50% of the energy is sort of lost in the system as heat. And so having some kind of active cooling is important for that as well.
Right. And this is for tissue ablation, actually destroying tissue. So probably a lot of the neuromodulation applications are much lower intensities and maybe don't require cooling. Is that right?
Yeah. Well, no, they aren't going to necessarily have as high intensity. You're absolutely right there. But it sure would be nice to have a system that has this sort of geometry that has multiple elements so that we could do the phase aberration correction across the skull and have the water for coupling. And while you have the water for coupling, having a little bit of cooling, it seems like it would be a nice thing as well. Mm-hmm. Yeah. All right. So let's get into sort of the heart of this lecture, which is talking about grading lobes. And before I get there, I just want to remind everybody about this really cool result. I was so excited about it. Then you remember I said, awesome, right? The idea here that's so great is that whatever your aperture is, that you can think of the far field as the Fourier transform of your aperture function. So what I'm going to show you is a way of thinking about what's happening in the far field, given our arrays, our aperture, which is split up into arrays. We didn't worry about that so much when we had single elements that we were modeling. But when we have an array, we are going to have to think about that a little bit more carefully, because I'm going to tell you about the grading lobes. Okay, so just to remind you about Fourier transforms and a few Fourier transform pairs that we saw previously. So one of them was that if you have a point source, then you're going to cut constant pressure in the far field. So the Fourier transform of a delta function is a constant number. And so this is what we saw before. If you have 2 point sources, then the Fourier transform of that, there's an interference pattern. The Fourier transform of that is a cosine. And so that's what we saw before when we did our simulation. And the last one we saw before was that if we have a series of point sources that are closely spaced together, we could say that's sort of a rectangle. Our aperture is a rectangle, and if that's our aperture, then what we're going to get is a sink. So the Fourier transform of a rectangle is a sink. And a sink is, of course, just the sine x over x. All right, and so that's what we saw before, where we did the simulation with multiple points spaced very, very close together. We saw that there was that main lobe, and then there were these side lobes that were much, much smaller, these side lobes. Okay, so in terms of Fourier transform pairs, now again, don't worry about this if this is not something that you're familiar with. There are some key concepts that I want to get across, and getting the gist of this is really important. Some of you are going to understand this, and that's fine. If we have a homework on this, then I'm available, and Emily is available also to help. But let me remind you what we've talked about so far. A few Fourier transform pairs. If you have a delta function, then the Fourier transform of that is a constant. If you have a rectangle, Fourier transform is a sink. if you have a cosine, Fourier transform is 2 delta functions. You know, we talked about it the other way. Your point source was 2 delta functions, and then in the far field, what you got was a cosine. But you can go either way with these. They go both ways. All right, so I want to talk about a couple more. One of them is the comb function. And this looks kind of like a comb. Like instead of a single delta function, you have multiple delta functions, right? So there's a reason why it's called a comb function. If you have multiple delta functions and they're shifted, like shown in the figure here, then the Fourier transform of a comb function is simply a comb function. So that's kind of easy to remember. You know, it's a different size comb function. It may be scaled compared to the first one, but it's still a comb function. So that's what's going to give rise to the grading lobes, as you'll see. All right, and the last one is a convolution, the last concept I want to express to you. So if what you have over in one space is the multiplication of two functions, and over here what we have is that comb function, and then we multiplied it times a rectangle, then what we're going to have when we Fourier transform that is going to be the convolution of the Fourier transforms of each of those. So we take our comb function, and then it's going to give rise to a comb function, which was multiple delta functions. And then we take the rectangle, and the Fourier transform of the rectangle is a sinc. And the convolution just is saying that now we're going to see a sinc at the location of each of those rectangles. And so that's what we see, is that those sinks that are now repeated. All right, now you're starting to get into, start maybe thinking, and I'm sort of previewing here, of why having multiple elements on our transducer is going to give rise to extra lobes in our beam. Okay, so we've talked about the comb function, and we've talked about what a convolution is. So at this point, I'm going to now walk through the grading lobe, sort of the derivation for the grading lobes. You with me so far, Keith, on what our Fourier transform pairs are?
I'm with you.
Okay. All right, take a deep breath. All right, here we go. So again, what we're going to talk about is this is our aperture. It's multiple elements. Each one of them is going to have some width. They're going to have some spacing. There's going to be a gap between them. The spacing is going to be the pitch. And then what's going to be the Fourier transform of that? And that's going to give us our beam. All right, so let's build this up bit by bit. First of all, the whole aperture is going to be a rectangle. So we're expecting to, in the far field, there's going to be something that's sinc-like. But it's not a single element rectangle like we saw before in the last lecture, but instead we're going to split it up as multiple elements. Well, if each of those elements was just a single delta function, then what we would get would be a delta function in our far field. But that's not actually true, because we're going to get multiple elements but have a finite aperture. So we're going to multiply times a rectangle, which means that we're going to get multiple sinc functions in our far field. And then there's one step further to go. And that is that they're not actually individual delta functions, but they're going to have some width associated with them. And so we have basically a number of rectangles, and then there's some overall rectangular shape to the aperture. So now following through, what we had is the multiple sinc functions, but that overall shape now is also going to, the overall shape gives us the multiple sinc functions, but the fact that each element is a rectangle gives rise to the fact that there's this overall weighting to each of those sinc functions. So what we see now is that the main lobe is going to have the most energy. These are the side lobes over here. You can see my mouse, right, Keith?
Mm-hmm.
Okay, good. All right, so we got our main lobe with the most energy. We've got side lobes, which are going to be really small and close in. And then at some distance a little bit further away, we're going to see grading lobes. And this is where they came from. The grading lobe came from the fact that we have multiple elements, and each of them is not a delta function, but they have some width to it, and there's some gap between them. All right, these grading lobes means that now when we turn on our ultrasound beam, we're going to have most of our energy going along the main beam, some of the energy in the side lobes, and then a significant amount can be in the grading lobes. And that's not really all that great. It means a number of things, as we'll see. Well, this is if you sort of lay it out on a sort of a straight axis. Another way you could think about it is sort of as a function of angle. And so if you're sending the beam straight out, you've got your main lobe that's here at 0 degrees. And then at an angle to that, you're going to get these grading lobes, so maybe 60 degrees or whatever it is. And we'll talk about the dependence of that angle in just a moment. But this is another way of sort of plotting this, is just showing these grading lobes sort of as in the direction that they're pointing. And this is going to be really useful as we think about steering the beam. Okay, we saw this before very early on in the lecture prior to this. We said, well, what if there was 7 elements and each of them were just point sources? Then because there was a fair amount of spacing between them, we ended up with these grading lobes. We didn't talk about it too much at the time. We really just talked about the main lobe and sort of the characteristics of the main lobe, although they were pictured there. And you didn't ask me about it, which was good, because all I would have said was, hey, we're going to wait and talk about that later.
So
All
Kim,
right.
you mentioned, so it's the larger the pitch between these elements, usually the larger the grading lobes. Is that correct?
Well, the larger the pitch, the more problematic the grading lobes are going to be, because those grading lobes are going to move closer and closer towards the main lobe. Yeah.
So what's, and I'm not remembering, what's the rationale for not reducing this pitch as far as you can? Is there some relationship to the wavelength that needs to be adhered to?
Absolutely. That's exactly right. We're going to talk about what our design goal is going to be.
Okay.
But what's the limitation? You know, just being able to get really small elements and being able to take that crystal and saw it up into small elements. The other thing is that there's going to be a trade-off between wanting a large area transducer and how many elements you need to drive that. Because we already said that we want something that's going to be really big in order to get small focal spots deep. But if going really big means that you have to have, you know, 1 million elements, that's going to be prohibitive, right? And so ultimately, there's going to be a trade-off between number of elements, transducer size, and the pitch. Okay, so you've asked me some really important questions. So let me see if I can answer some of those in this next section, unless there's anything else you want to ask before I keep going.
No, I have more practical questions, but we can talk about that later.
Okay, good. All right, back to our Fourier transform pairs. So we've talked about most of these. The sinusoid is just like the cosine, except it had the, you know, the transform of the sinusoid is one positive delta and the other one's minus, and then they're imaginary. The other one is this one down here. And let me explain what this is. On this side, it's basically a phase as a function of time. So this is, F naught is a constant. And so this is just giving you, as time goes on, a linear phase. And so because this, what's in the exponent is the phase term. So we're going to have a linear phase in this space. And when you Fourier transform a linear phase, instead of getting a delta function at basically at 0, or at a delta function at 0, we're going to have a shifted delta function, so that it's shifted now by according to what that linear phase is. All right, this is called the Fourier shift theorem, and this is the basis behind how you can steer the beam. Because what we're going to see is that all we have to do is take our elements and we apply a linear phase to the elements. And then remember, we're going to get this nice beam in the far field that's a Fourier transform of our aperture function. And so if we've applied a linear phase, what we're going to get is just simply that beam's going to get shifted in the far field. So let me explain it a little bit more graphically as well. So I've set it up with 4 different situations here where we have 5 elements. We're going to start with the basic ones where we're going to have constant phase on those elements. Each one's going to send out a spherical wave. They're going to have some interference pattern. We're going to start seeing sort of a linear front, a wave front going straight out. And that's going to give us, in the far field, is a beam. Now, what you can do is you can phase those elements with a linear phase, so that now we're just adding the same a linear phase, so it's increasing as you go to the right. And those wave fronts now, it's as if this one came out earlier than this one and this one. You can see that the wave fronts now are angled. and we're going to get an angle to the wavefront. And in other words, in the far field, that the beam is now shifted. It's steered to the side. The beam in this case now looks like it's going to be, the same shape, the same width, but it's just steered to the side. So you just have to apply a linear phase across your elements in order to get a steering of the beam. You increase the amount of phase, that linear phase you apply, you steer the beam further to the side. So that's cool. Now, one of the things we've talked about prior is that we actually want to use the phase in order to give us a better focus. And so remember, that was so we have some curvature to those wavefronts. We get a focus that's going to be tighter. And you can actually just do these together. So now we take our quadrature phase that we've applied here, we add a linear phase to that. Maybe it looks something like this. And now we're going to get that focused beam steered to the side. All right, well, cool. That's how steering works. And that's really one of the most greatest reasons why to use an array, is that you can now steer the beam to the side. So if you say in the neuromodulation situation where you've set up that transducer on the head, and straight out from the transducer is not exactly where you want it to target, you could just use your array to steer it to the side. You could also do some steering in the depth direction as well. How the shape of that function, the quadrature function right there, is going to determine the depth direction, and then the linear phase is going to determine the angle of the beam. Okay, so what happens with those grating lobes when we steer the beam to the side? Well, we can go back to our math. Our aperture was a series of elements, each with some width, and the distance between them was the pitch. What we're going to do when we steer the beam to the side is we're going to apply linear phase. And when we Fourier transform that, we're going to get a shift of those individual sinc functions. So instead of being straight in the middle of the sinc envelope, now that those sinc functions are going to be shifted to one side. And you can see that the main lobe that we're looking at is now decreased in amplitude, and that grating lobe is increasing in amplitude. Well, if we go back to this drawing, then it's just kind of a way I like to think about it is that these lobes are going to circumscribe around an oval. So the grating lobe is going to go off in some direction, and then as you steer the beam to the side, then that main beam is going to go along that oval. It's going to start decreasing its amplitude, while that grating lobe is going to, again, go along the oval, and it's going to increase its amplitude. So you could imagine you could be in a situation where you're steering it so far to the side that that grating lobe is actually of equal amplitude as the main lobe. And then that's not such a great situation to be in. So grating lobes are something we definitely need to take into account and think about. All right, so a lot going on here in this lecture. We're getting near the end. One of the things I wanted to talk about is the angle of the grating lobe and its dependence. And so what we see is if we define the angle of the grating lobe as the angle from the main beam, that the angle of the grating lobe is given by the sine inverse of some number of wavelengths over the pitch. Okay. So what that means is that as we change the pitch, we can change the angle of the grating lobe. So all we really want to do is make the grating lobe angle go to 90 degrees. And so then it would be over here. And so it's not really going into our subject. And then in order to make the angle go to 90 degrees, we do that by making the pitch less than the wavelength. And so then now you can see that when you're making the transducer, that depending on what your frequency that you want to use, that's going to determine what the spacing is between the elements in your transducer.
And Kim, do you know the manufacturing limitations at present? Is there a sort of a maximum frequency we can go to, because we simply can't cut a small enough pitch to make that work?
Yeah, I don't really think that for neuromodulation that we're limited by being able to cut the elements really small and get them close together. I think what we're going to see is that we're going to be more limited by how many elements is it feasible to drive a transducer with. You know,
Mhm.
that sort of question of, well, you could easily put something together that would have like 1,000,000 elements, but then it's just really not feasible to drive 1,000,000 elements. You know, wanting large areas, but, you know.
Right, and I don't know if this is the time to talk about it because we already did hardware, but what are the typical ways that you apply phase delay in a sort of software hardware manner?
Mhm.
Because we're not using individual function generators for each element, are we?
Um, you know, that's a good question. And so, um, uh, you know, it used to be with the diagnostic ultrasound, or it may still be true, that with the diagnostic ultrasound systems, that there's actually a hardware that will delay the pulse. But as I mentioned before, with the continuous wave, you do it more in software where you set each of the element phase. But yeah, I'm not sure I'm totally answering your question there. Let me think about how to answer that.
I'm not sure I know either. I've seen different approaches, but we can talk about that during discussion.
Okay, let's see. Do you have other questions about grading lobes or?
Yeah, one last thing. I think so. There's another approach of course, getting these grading lobes to 90 degrees really gets rid of the problem. But if you can't, you can also change the distribution of elements to reduce grading lobes, right? Like there's a mathematical sort of symmetry when you evenly space them that naturally creates the lobes. But what if we just randomly space them?
Yeah, no, you raise a really good point. So, uh, what we talked about was you know, of course, the beam is the Fourier transform of our aperture. And if you have something that's very regularly spaced, like Keith mentioned, and then we came up with exactly why the grading lobes look the way they do. But you could imagine a situation where it was a different aperture function. And let's say you did have them randomly spaced. Then what you would see is, again, it would be the Fourier transform of this randomly spaced aperture function. Essentially what would happen is all the energy that goes into these grading lobes would be spread out more randomly across the image. So there wouldn't be sort of grading lobes that are, you know, individual lobes that are as high, but it would be like a little bit more background across the whole image. In some situations, that's probably preferable, because if you're talking about, you know, something that's a threshold effect, then if you have lots of energy that's sort of sub-threshold, then that's probably just fine.
Hmm. It's probably better with tissue ablation where the threshold is more well defined. The class will find with neuromodulation, it's often like sort of a long gradient effect where, there's not some instantaneous point where you just start getting cells to fire, but really that their activity can ramp up or ramp down over time.
Hmm.
So maybe not quite as useful for neuromodulation.
Okay, well, I look forward to hearing more about that, because, you know, often we tend to think of it as a little bit of a threshold effect. So this is something we definitely are going to need to draw out in our future lectures. Okay, well, let's conclude for today. Oh, wait, I seem to have one or two more slides. Grading lobe artifacts. Yeah, so let's say you're doing diagnostic ultrasound and you have your transducer and you're imaging across this line, and there's an object over here. Maybe it's you know, like a piece of bone that's giving you a huge reflection, and it's right in the grading lobe. Then you're going to end up getting a big echo coming back from it. Even if these grading lobes are smaller in amplitude than the main lobe, you might get a big reflection coming back. But the computer doesn't know that it was in the grading lobe and is just going to paint that in the main part of the image. And so you can end up with artifacts in the image due to grading lobes. For us in therapy and neuromodulation, it means that we're putting energy where we don't want it. So we may have an effect somewhere else in the body that we're not interested in having that effect. So that's why we're particularly interested in it.
So, from speaking with all of you, we got the impression that you wanted to learn how to actually get to have your own array. And one way to do that, of course, is just like going out and building it. And we're not here to tell you you shouldn't do that. Like, it's possible to build your own array. But then you might need to acquire a huge driving system that has an individual channel for each, and it can get really expensive and really complex really quickly. So Kim and I talked about it, and we thought the more practical thing to do was to teach you almost how to select an array for your particular application. Because looking at designs and understanding what you need is, one way that you can just go to a manufacturer and say, hey, I need this built, and they may have all the hard tools to get that done for you. And if you're really lucky, or maybe even more commonly now, there might be an array that already exists that can do what you're looking to do. And then you can just buy it off the shelf and you're ready to go. Kim, is identifying an array that is good for you an easy task?
I think it's a bit complicated. There's just a lot of concerns in picking an array, picking frequencies, aperture size. So it's a little complicated how to figure it all out. I'm looking forward to seeing how you sort of frame the question.
Okay, and I appreciate that, because if she said it was easy, that would have hurt me right here. Kim and I have actually in the past gone through considerations of all the different facets of an array, and she's already taught you just now that there are characteristics of the elements, the aperture, the operating frequency. So we'll just start with an individual consideration. And let me just say, what is the operating frequency that you want to use for your array before deciding anything else? And I just want to demonstrate how complicated this can get. So let's just say you're talking to your team and you're saying, well, what happens when we increase the frequency that we're using? And as you now know, right off the bat, you're starting to lose your transmitted power at the focus, because attenuation and absorption is going to be greater at a higher frequency. But you do know that your beam size is also getting smaller, which if your brain region is really tiny, that's a good thing, and we'll call that better. And you can go down this huge list of trade-offs, a lot of things you've just learned about, including grading lobes and maybe mechanical index. So how do you take this multifactorial, high parameter space system and evaluate to identify even this one parameter, frequency? So Kim and I, when we talked about this back in the day, thought it would be a good idea to just say, well, take all the things you can think of and rank them. And that's what we did here. We literally went through and said, what's most important to us? And when we were thinking about it, transmitted power, beam size, and absorption at the skull were paramount above all of these other items at the time. So I guess reduction of parameter space whenever you're trying to decide on your array design might be a good way to start. And then once you've ranked it, you can start to iterate through these different outcomes and to try to look for a balance between them. Kim, what are your thoughts? Is this the way to go, or are we just coming up with something that works? And there's never one path to the end.
Yeah, it's a good start. I'm also interested to see where you're going from here. So let's keep going.
Yeah, we can jump forward. So I won't bore you with too much more of this. Okay, so changing frequency. One way to assess this frequency is to just simulate it and to look at the outcome of the simulation. And here you can see two things that are happening. So if we just have our beam at its natural focus, so we're using our array to steer forward orthogonal to our plane, as we increase the frequency, you can see that our beam size gets smaller. So that's a good thing. Okay, so we've improved one feature as we increase frequency. Now we can ask the question.
So I'm assuming you kept the aperture size the same and your distance between elements the same. Mm-hmm. Is that right?
Yes. So everything was fixed here.
So now we can see a difference in the location of the grading lobes because you kept the spacing the same.
Mm-hmm. Mm-hmm. Yes, so now we can look at grading lobes. And grading lobes, as Kim's already shown you, become more apparent as you steer your beam laterally in space. So here we have our lower frequency where, there is a grading lobe, but it's very small compared to our sort of main focus here. Whereas if we look at a higher frequency for the same array and the same focal point, we start to get a very substantial grading lobe. That's almost half of the power at our main lobe. So again, we have these two conflicting outcomes, and you have to consider for yourself what is ideal. So another way to think about this when you're working with the manufacturer or your simulations person, and this actually was the result from work with Sonic Concepts, is to say, what if we measured our peak at our optimal steering point, which here, I know this x-axis is sort of reversed, but here it's at around 2 centimeters relative to this x-ray. So this is where our optimal focus would have been. But if we move it across space, so we perform a spatial sweep, we can ask, how has that focus at this new steering point compared to our focal max, which is at our optimal steering? And here you can see that if the two are the same, you have a value of 1, because they are indeed the same thing. But as you steer the beam axially or laterally, you start to reduce this ratio. And if you get too far away from your focus, like up here, for instance, your beam is now only 0.2 as a fraction compared to your optimal steering point. So when I look at a map like this, it just essentially tells me, how far can I go out in space before I start to have really, none of the main power and none of my main, effect. So I don't know, Kim, what are your thoughts? Is this a useful plot to look at?
Oh, absolutely. That's a nice way of looking at it, because it kind of says, well, if you're, how much latitude do you have to steer it? And so it kind of gives you a nice depiction of that, and saying, in this case, it looks like you can go plus minus 2 centimeters, and that's about it.
Yeah, and it draws this other important sort of question you have to ask yourself, is like, people always ask us, what is enough? Is 50% enough? Is 20% enough? So, that might be different for you, and you have to find out for yourself. Okay, and this also allows us to consider the off-target pressure. So if I'm not at my optimal power deposition out here, where is that power going? So you can actually inverse this problem and ask, what is the peak at the grating lobe, or our sort of off-target lobe, versus the peak at our focus? Okay, so let's go back to our focal peak here, which is at 2 centimeters on the x-axis. So here we have a value that's somewhere around 0.2 to 0.4. It's very, very low. So that means that wherever the peak grating lobe is a very small fraction of our focal peak. However, as we steer axially or laterally, the grating lobe starts to become almost as strong as our focal peak. And when we get outside here, they're essentially equivalent. So that should allow you to think about this system. That would mean that if this was red, our grating lobe would also be red. So your off target and your on target are essentially equivalent. And that might be really bad, especially if this other brain region or target does something that you don't want to happen in your treatment. And one last way to look at this, you can actually overlay these two systems at once. Here are red lines denote sort of I forget what you would call this sort of plot. It's almost like a topographical map, where anywhere within this red line, your grating lobe is at 0.32 or less of the power from your main lobe. And the black lines describe how much your peak focus is relative to your sort of off targets. So you can see as we go axially, your black lines become less as a ratio and your red lines become higher. And when you get all the way out here, your gratings are at 0.7 and your black are less than 0.5. So it's just a way to look at them simultaneously. And then you might go to someone that you're working with and say, hey, can you provide me this type of map for different array configurations, different frequencies, all kinds of parameters, and it allows you to assess these things. Kim, any thoughts or questions on that?
No, it's kind of an interesting plot there on the right, but it's kind of confusing.
Yeah, when you get used to using these and looking at them a lot, it starts to become a little easier, but there's a lot going on here. I agree, which is why I started you with sort of the single dimension plot.
Yeah, the color plots are just a little bit easier, and it's going to be very clear that if you stay near the natural focus, then you're going to do pretty well. It's just if you know what your tolerance is in terms of how much you can power you can lose at the focus, and then those are easy. The other one, Yeah, it's a bit tricky
It's a
understanding
little
that one.
tricky. Yeah,
Yeah.
we had similar complaints when we started. And as always, know what you're trying to reach. So the people you're working with will always say, well, like, how much are you willing to give up here? And often Kim, will use the terms down to -3 dB, down to -6 dB, sort of a question of how low you're willing to go. Again, I'm borrowing something from a partner of Sonic Concepts, a company called Neurofuss. So this company explicitly designs transducers for ultrasound neuromodulation, and they're a product of BrainBox, who Kim and I know very well. So I just put this slide in here so it could kind of show us properties that you might see in a diagram or a schematic. So here they're giving you the diameter, so you can start to think about sort of your aperture. You get height, so like, okay, well, how would I hold this thing? What kind of packaging can I fit it into? And then they also give you a down to -3 dB focus. So when the pressure falls below 3 dB of your peak, you sort of just draw a line around that. And that's a common way to look at different transducers. And because this is a multi-element ring array, so this is a slice through space, sort of an orthogonal slice, but you can see these different elements. And by changing the phase of each one of these rings, you can actually move your focus to, to be closer or to be further away from your annular ring array. And Kim, I think the trust system that we've already shown the students was a ring array just like this, or was it different?
No, it is not a ring array. It's a circle, but it's got elements that are laid out on a kind of Cartesian grid.
Gotcha. So it's a grid array. Okay, so not quite like this, but this is maybe a different type of system you might want to use. And I sort of put this in to just have an open discussion with Kim, and maybe you can look at it yourself and think about the trade-offs. But here are 4 different models that Neurofuss makes, and the CTX, the number value here, is basically referring to the frequency, the operating frequency. So here you can see that we're increasing the megahertz value. And I'm going to jump all the way to the end here and just ask you to consider what happens. So here we're looking at our focal axial length. So how long is this beam in space? And one thing that you can appreciate is that it quickly drops off. So the focal length gets much smaller. So if we're just considering that, Kim, great. Why don't we just go crazy with the frequency? Why don't we go above 2500? So Kim, I'll ask you to look at this comparison chart and to ask you why higher might not always be better.
Well, in this case, I think the 2500, I'd be hard pressed to think that it would work in humans at all, just because if your focal length is 2 millimeters, then there's no skulls that are even that thin. Mm-hmm. So you're certainly not going to go higher than that in humans. Rodents, it might work just great.
Right, maybe so. Maybe this transducer was actually designed for small primates or for smaller animal models. Mm-hmm. And you can even see that in our distance to the focus. So here, the distance to the natural focus is much smaller than the CTX 250. So Kim, let's say we had a person with a thin skull, or even not a thin skull. What might this transducer be useful for versus our CTX 250?
Oh, you know what? I misread it. So the distance to the focus is what I was thinking was the focal length, but all the way over on the right, that's a different parameter, axial length.
Yeah, I didn't want to stop you short. Yeah, that's just the size of the focus.
Yeah. Okay.
But what you were thinking is distance to the focus, right?
Yeah. Okay, so that's really interesting. So 1.3 centimeters. So you could think about maybe trying to get to the cortex in a human at 1.3 millimeters. Centimeters. It'd be a little hard, and there'd be just so much absorption at that frequency that would be really hard.
Yeah. So those are even just a few trade-offs, and it's difficult to say if they're sort of reflected in these peak power in watts, because they've compensated so that your focal intensity in a free field is 30. Well, I guess, okay, so Kim, do we talk about what free field means when you're assessing these sort of grids?
I don't think we've talked about that yet, but I mean, that's like if you make a measurement in a water tank.
Mm-hmm. So this is probably not a very good indication of what would happen when you stick a skull in there. So Kim already mentioned, even though it's 30 watts per centimeter squared in free field in water, it's going to be way, way lower in with the skull in place. Whereas your 250 might not be affected, much at all. Okay, so what else is there to look at here? So yeah, I think that covers everything. And I think during our discussion, we hope you ask a lot of questions that are personal to your interests about, oh, well, how can I think about this parameter? And how can I design an optimal array for that? And maybe even for your project, you come up with an algorithm or something for optimizing your array designs. Kim, any final thoughts on this? I hope this was useful.
Yeah, it was pretty interesting. Hey, is this information that's available on their webpage?
It is, yeah. And I think they'll even have plots like these available for each one of these transducers, since they're axially steerable. And maybe you want to push them even beyond, the steering range that they're talking about here.
Mm-hmm.
Okay,
right,
so let's wrap it up there.
Okay. All right, well, that's cool. Thanks a lot for doing that. Okay, let's conclude this one. This has been a long lecture, but action-packed. We've talked about single element transducers, planar and focused, characterization of the focal spot, focal depth, F number, width, and then the length of the focal spot. We've talked about arrays. We've talked about grading lobes and side lobes. Well, side lobes come up with single element transducers as well. Grading lobes come up when you have arrays. And we've talked about what happens when you steer the beam with an array, and how those grading lobes increase as you steer the beam off to the side, and then how the manufacturers have these color maps, these heat maps to describe that effect. So action-packed. Have we missed anything here, Keith, or should we call it a day?
I think we can call it a day. I'm looking forward to the students' comments and questions on this stuff.
All right.
Hopefully we did a good job with it.
Okay. All right, good.